Hello everyone and welcome. In this session, we are going to dive into the critical topic of password security. We'll explore how passwords should be stored and what protection mechanisms can be applied. Let's get started. Password security is of utmost importance in protecting our digital lives. One of the key challenges is that passwords remain the primary method for authenticating users. Storing passwords in plain text makes systems highly vulnerable to breaches. Many users reuse passwords across different services, so a breach in one service can compromise many others. Weak passwords can be easily cracked using brute force attacks. Compromised credentials can give attackers access to multiple systems and sensitive data. Here's a comparison between storing passwords in plain text and storing them securely. On the left, we see an example of bad practice. The code shows a function that creates a user and directly saves the password provided by the user in the database without any encryption. Storing passwords in plain text is extremely risky. If a database is breached, all passwords are immediately compromised. This approach provides no security against unauthorized access. Now let's look at the good practice. The code shows how a password can be stored securely. Before saving the password to the database, a unique random salt is generated. Then the password and the salt are passed to a cryptographic hash function. This hash function generates a hashed password, which is then stored in the database alongside the salt. This way, if the database is compromised, the attacker will not be able to directly read the user's passwords. Secure storage uses cryptographic hashing with unique salts to protect passwords, even if the database is compromised. Cryptographic hashing is the backbone of modern password security. It involves several key properties that make it suitable for securing sensitive information. The first property is that it is a one-way function. That is, it is computationally infeasible to reverse the process and obtain the original input from the hash. The second property is that it is deterministic. This means the same input will always produce the same output hash value. The third property is avalanche effect. A small change in the input will result in a drastically different output hash. The fourth property is collision resistance. This means it should be extremely difficult to find two different inputs that produce the same hash value. The fifth property is fixed output size, meaning regardless of the input size, the hash length will always be constant. It's important to note that hashing alone is not sufficient for password security. It must be combined with salting and appropriate algorithms. To further protect the passwords, we make use of a technique called salting. A salt is a random value that is added to each password before it is hashed. This process protects against rainbow table attacks, which are precomputed hash tables that attackers use to crack passwords. Salting also ensures that if two users have the same password, the stored hashes will be different because each password has a unique salt. This makes batch attacks where multiple passwords are cracked at once much more difficult. Here is an example of how to store a password securely with a salt. First, we generate a random salt using cryptographic functions. Then we hash the password with the salt using a key derivation function, specifying the number of iterations, key length, and the digest algorithm. The salt and hash are then stored for authentication purposes. Now let's compare different hashing algorithms. On the left, we have recommended algorithms like Argon2, bcrypt, pbkdf2, and scrypt. Argon2 is a winner of the password hashing competition, which makes it highly resistant to attacks. bcrypt is designed specifically for password hashing with built-in salt and adaptive cost. pbkdf2 is a National Institute of Standards and Technology, NIST, approved key derivation function with adjustable iteration count. scrypt is a memory hard function designed to be resistant to hardware attacks. On the other hand, we have outdated or insecure algorithms such as Message Digest 5 MD5, Secure Hash Algorithm 1 SHA1, and SHA256 or 512. Message Digest 5 MD5 is broken and vulnerable to collision attacks. Secure Hash Algorithm 1 SHA1 is deprecated and vulnerable to collision attacks, and it is too fast. The SHA-2 family is cryptographically strong, but they're too fast for password hashing. On the right, there is a comparison table between the algorithms, and it describes their security, performance cost, and memory usage. This slide illustrates a secure authentication flow, detailing both the registration and authentication processes. During registration, the system first takes the user's password. It then generates a random salt and hashes the password with this salt. Finally, it stores the username, salt, and the hashed password in the database. During authentication, when a user attempts to log in, the system retrieves the stored salt associated with that username. It then hashes the input password using the retrieved salt and compares the result with the stored hash. If the two hashes match, access is granted. If they don't, access is denied. In addition to this flow, several best practices should be followed. Use constant time comparison functions to prevent timing attacks. Implement rate limiting to prevent brute force attacks. Add account lockout after multiple failed attempts. Use secure connections such as Hypertext Transfer Protocol Secure, HTTPS, for all authentication processes. Implement multi-factor authentication for sensitive systems. Apply key stretching with sufficient iterations. Store authentication tokens securely with proper expiration. And regularly audit and update password security measures. Here's a quick summary of what we've covered. Never store passwords in plain text. Always use cryptographic hashing. Always use salting to prevent rainbow table attacks. Choose modern algorithms like bcrypt Argon2 or PBKDF2. Implement defense in depth with multiple security measures. Some common pitfalls to avoid. Using outdated hash functions like Message Digest 5, MD5, or Secure Hash Algorithm 1, SHA-1. Implementing custom cryptography instead of proven libraries. Forgetting to use constant time comparisons for hash verification. Neglecting additional security measures beyond hashing. For those looking to dive deeper, here are some valuable resources, such as the Open Web Application Security Project, OWASP, Password Storage Cheat Sheet, National Institute of Standards and Technology, NIST Digital Identity Guidelines, and Password Hashing Competition. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.